final speaker today will be presenting virtually via Zoom. Our last speaker is Kao Bache. Kao is a PhD student in computing and mathematical sciences at Caltech, advised by Houman Owhadi. His main research area is game theoretical uncertainty quantification and Gaussian process regression, both from a theoretical point of view and with applications to the physical sciences, including collaboration with scientists from the machine learning and uncertainty quantification groups at NASA Jet Propulsion Laboratory. Before joining Caltech, he graduated from Universitat Politècnica de Catalunya with a double degree in mathematics and engineering physics as part of the CFIS program, and he was a research intern at the Center for Data Science at NYU for 9 months.
Thanks for the introduction, and hi everyone, and my apologies for not being here in person. Today I'm going to talk about uncertainty quantification for Gaussian processes, and particularly in the setting of using Gaussian processes for model emulation. I'm going to start with a real motivating example that we're working in collaboration with JPL, where we have radiative transfer models that map the reflectance to radiances, and this is what we call the forward problem. But we're usually interested in the inverse problem, in which we measure the radiances y, and we're trying to infer the reflectance from it. And the standard method, or the previous method that was used for this, was big lookup tables and then doing linear interpolation. This was not only expensive in high dimensions, because for the lookup tables were just the function evaluated at certain parameters, but also they do not provide uncertainty quantification. So one of the current projects at JPL, in collaboration with my advisor group at Caltech, is to replace these lookup tables with Gaussian processes with learned kernels. And I'm going to be more precise about what I mean with learned kernels, but here the summary is that you can see in this figure, which is the root mean square error of the different Gaussian processes in blue, orange, green is significantly smaller than the lookup tables, which is in black. So they provide like better emulation, and they also provide uncertainty quantification. I want to acknowledge the collaborators that have been mostly working on this project. I've been working on more theoretical projects that are tangential to this. So today I'm going to focus on the uncertainty quantification component of using Gaussian processes as emulators, which again was one of the main advantages when you compare to this previous method that was being used for this problem. So I'm going to start with a little bit of introduction about the uncertainty quantification that Gaussian processes provide. Gaussian process is nothing else than prior in the space of functions that tells you that if you evaluate at a finite number of points, then the distribution will be Gaussian. And usually what you do is condition to the sum of the data that you have seen. And then for any unseen data, like the distribution will also be Gaussian. So for example, in this image on the right, we see one of the most classical settings of GPs, where we have these UQ bounds in blue. And usually what we mean by Gaussian processes provide UQ is something like what's mathematically written in the bottom of the slide, where if the root function was sampled from a GP, which can be seen as a probability distribution of this over functions, then this function sampled at a particular x will be in this interval with certain probability. And this is just the classical interval of the classical confidence interval for Gaussian random variables. What's important here is that in practice, we need to choose a kernel or covariance function k. And this kernel and covariance function essentially shapes and gives the size of these uncertainty quantification intervals. So what I'm going to focus today is, since k is something that we don't know in practice, but we learn, how can we make confidence intervals in the setting in which we don't know k and we have to learn it? So what we usually do is use a parametric family. Here, like the kernels are parameterized by some theta in Rk, and we learn which of the kernels to use in this parametric family by some method that uses the data. This could be something like cross-validation, maximum likelihood estimation, hierarchical base, which would account to putting a prior over this theta. But most importantly, if we learn kernel k theta star, the UQ that we're going to get out of using that kernel will only hold and will only be true if this was the real kernel that generated the data. Since this is too much of an ask, today we're going to propose a method that does full UQ, so that accounts for the uncertainties on the learn parameter. But it only depends on the assumption that the function was generated by one of the parameters in the family. So we're going to learn one kernel, but we're not going to assume that this was the true one to provide UQ. We're just going to assume that the true kernel was somewhere in the family. And here, to do that, we're going to combine two types of uncertainty, what I call aleatoric uncertainty, which is the uncertainty that depends on the randomness of the Gaussian process itself, and what we call the epistemic uncertainty, which is the uncertainty on the learn parameter. So combining both, we can give final uncertainties on the predictions. So I think this is going to be better seen with this running simple example, which is the one that was in the introduction. We want to regress this 1D function that we have observed at certain points with a kernel, in this case, a family of matern kernels. But the expression is not that relevant. What's only relevant for us is that it depends on two parameters, this L and length scale L and amplitude A. And they both will change how our predictions, and I guess importantly here as well, our UQ look like. So here we have like an AL diagram. So you can think about the choice of one kernel as just one point in this diagram. And as you move around, hopefully the animation can be seen correctly, but as you move around this A and L diagram, both your prediction as a conditional mean and UQ bounds change, and they can change quite a lot. So it's important to understand what A and what parameters of these values A and L we actually need to consider in order to do UQ. One possible solution to that is a fully Bayesian treatment, as I briefly mentioned before, which would include selecting a prior P of theta over probability distributions of theta space, and then approximating the posterior distribution. Once we have the posterior distribution, given a new data point, we can go through the classic Bayesian inference pipeline and just provide uncertainty for y-test. But here there's two drawbacks that might happen in some applications, and it's the reason that they motivate a new approach. First of all is that the prior needs to be chosen, and this is an extra assumption that affects the UQ. Of course, if the prior is chosen for a particular application, then this is like perfectly fine. But what can also happen, even if you know the prior, is that the posteriors and computations of integrals like the ones we have on the screen can be expensive to compute. And even sometimes you have to sample through MCMC methods, which can be slow and can suffer from the course of dimensionality. So we're gonna do an alternative approach that starts with building a confidence set in this parameter space. So here is the same diagram that we had before with like a square with A and L. And what I'm going to do is restrict A and L to those points that have a likelihood at least alpha. So here I can compute the likelihood in the same way that I was doing here, and the likelihood is given by the GP model. And what I'm going to do is compute the MLE, put it in the denominator, and then threshold theta if the likelihood divided by the likelihood of the MLE is greater or equal than some alpha. I'll get into how to choose alpha, but for now, just think about this image where as alpha goes to 1, you shrink towards the MLE. As alpha goes to 0, you would eventually recover the whole space. So if you pick alpha, this gives you a region of this parameter space that you have to consider. The way to choose alpha is such that this set that we have constructed here has a 1 minus beta frequencies coverage probability, which means that in the worst case, the long run probability of the set not containing the true parameter is upper bounded by beta. So this means that the probability of being inside the set will be at least 1 minus beta. There's two possible approaches for this. We have some technical results, but essentially in the low data regime, you can compute samples of this distribution cheaply. You can do some kind of data-driven quantile estimation. But if you're in the large data regime, we prove asymptotic results, which essentially look like this, which has to be thought about as a way to pick alpha for a given beta. Beta is something that will be chosen by the practitioner, which will be something like 95%, or 1 minus beta will be 95%. And then this theorem tells you under like a high data regime how to pick alpha as a function of beta. And this can be thought as a Gaussian process version of Wilks' theorem, which is a classical theorem in statistics. Here we see for the running example that even the asymptotic approximation is accurate. Even though we're in a very low data regime, we have less than 10 data points, but still the difference in CDFs between the empirical distribution and the asymptotic distribution is very small, meaning that using the asymptotic approximation, we would not be incurring much error. So once we have picked this set, the theta x of alpha that depends on alpha, I'm going to define an interval that contains both epistemic and aleatoric uncertainties as follows. This interval that depends on gamma and alpha. Alpha is the parameter that I've mentioned before that controls this epistemic uncertainty, and gamma here is the standard number of a standard deviation from the mean the standard deviations that you're away from the mean. So this combines both, and essentially defining this function, which is just the mean plus minus gamma standard deviation. I'm going to take the worst case over theta in this set. There's also an interpretation of this result as Bayesian posterior means under worst case priors. But I'm not going to go in depth into that today, but essentially like these intervals can also be derived as a form of Bayesian inference in which the person adversarially to you by playing a two-player game. I think the image that's important to have is that, for example, if theta x of alpha were to be just two parameters, you're taking the worst case with this interval both in the top and the bottom. So if you see this, where when the red line is over the blue line, we take the red line on top, and similarly for bottom, such that no matter which one of the true ones is no matter which one of the two theta 1, theta 2 is the true one, we're going to have coverage. So you can think about this interval as being the continuous version of this, in which instead of just two parameters, we're going to sweep through all the parameters in that set. And the important thing about these intervals is that we can prove some coverage just using the assumption that one of the models in the family is true, not necessarily the one that we have estimated by MLE or any other method. And we can prove that this interval satisfies the following bound, in which the worst case frequentist probability is bounded by the product of two terms. One of them is 1 minus beta, which is the epistemic coverage, and the other one is the aleatoric coverage. And this was the same term that appeared before in the setting in which we actually knew, or we actually assumed that we knew the kernel that generated the true function. So what we see here is that we're paying some kind of price of ignorance, in which our probability bound will be worse just because of the fact that we don't want to assume that we know the true kernel. Here's a diagram that can help about thinking on the whole process. There's two parameters, and it's important to say that these two parameters, beta and gamma, can be chosen by the practitioner, and they model how much we trust our decision in like different axes. Choosing beta essentially lets the practitioner decide how much the output of MLE as a way to choose the parameter is trusted. So if we want to be more robust about theta dagger, because we maybe don't believe that the true parameter, the parameter found by MLE is more accurate, we can move to the right in this diagram. If we want to be more robust about the GP realization, which means that we believe that we might have observed outliers in the data, or data that was far away from the mean, we'll move up in this diagram. And once we get into the boundaries, Here, for example, the blue boundary is just choosing theta equals theta MLE. So the bounds become fully aleatoric, and the more like classical bounds that just depend on gamma. On the other side, we do a worst case over the whole parameter space, which means that we don't use the data at all. And in the bottom side, we believe that we have observed exactly the conditional mean. So the bounds become fully epistemic. Like the bound will not depend on the randomness of the Gaussian process. It will only depend on our lack of knowledge of theta, the true parameter, which in practice looks something like this. We see here in red the conditional mean of the Gaussian process, and this is the same setting as the running example. In blue, we see the standard covariance bounds that we could get from using something like MLE and then just using that kernel to do the covariance bounds. But here we want to argue that that is not enough, and that doesn't really paint the whole picture, because we don't really know that the kernel that we have chosen with MLE will be the right one. So we have to pay this price of ignorance by essentially expanding these bounds to these aleatoric and epistemic combined bounds in green. And again, the two parameters, the epistemic coverage and the aleatoric coverage, can be chosen. And if we focus on different parts of the diagram, different parameters will behave differently. And here you can see like how these bounds change as you move through the diagram. And the main take-home message here is that the two parameters can be chosen independently, and the UQ that you get out of it will depend on your choice. And again, I think of this choice as kind of an application dependent that navigates a trade-off between accuracy and robustness. If we go to the other side of the diagram, here we're going to see how the bounds shrink. In particular, the blue bound shrinks to the red line, and then the green bound shrinks to the blue line, depending on the direction that we're picking this parameter from. So I think that there's a main take-home message that goes beyond this Gaussian process setting, in which any UQ method can be thought as a box. It receives some assumptions and then it outputs some results. And if we have different UQ methods that can be applied to a problem, it's not really the one that gives the tightest UQ, the one that will be best, because that might be using lots of assumptions and some of them might not be true. So I would like to argue that the best UQ method is the one that best uses the available information. And in this case, we should be willing to pay a price of ignorance, which it's exemplified by the blue bounds growing to the green lines, just because we don't know exactly the true parameter. So in this method, we only use this information. So we only use information that the true parameter is here, which again might still be wrong, and the Gaussian process regression model might still be wrong. And we have to acknowledge that we're making this modeling assumption, but it's generally more part of a general line of UQ work that we're developing that uses this idea of use what you know and worst case over what you don't know. In this talk, what we know is that theta dagger is in the parameter space, and we also know the data from the GP, so we use that. And what we don't know is that the learned parameter is the true one, and the prior from which this parameter was sampled, if you want to think about the Bayesian interpretation. So we use what we know to find a reasonable guess for this space, and then we take a worst case over priors on that space to make the predictions. So that concludes my talk. We have a preprint here with the general setting of uncertainty quantification with game theory that computes this kind of worst case priors in kind of the general model. And we're preparing a preprint with the content of this talk that focuses more on Gaussian processes. Thank you. I'm happy to take questions.
Okay, so if you have a question, how about you step up to the mic so that you can hear your question clearly. Does anybody have a question for Cal? Yeah, just right in front of the computer. Just insert, yeah.
Okay. Thank you for the talk. Just a question on if you're looking in the future to capture the uncertainty on the, looks like the covariance function. And any thoughts you have on how that might factor into what you showed today?
What do you mean by uncertainty in the covariance function?
If I remember right, on one of the earlier slides, you showed a function for that, and there are other models that could be used for the covariance function.
Yeah, absolutely. Yes. So that's a very good question, because here in my running example, I've just used a parametric family of covariant functions, where in practice, even though you might not know like the true parameters of this family, there's another layer of uncertainty, which is you don't know which parametric family to use. So one of the good things about kernel methods is that you can add together like different covariance functions, and you can think about trying to also learn weights before each of the families. So you can think about the composite kernel, that it's the sum of different families of kernels, and then like the coefficients in front of it, like if you learn them, will tell you which of the covariant functions will explain more the data.
Yeah, exactly. And I guess you would expect some of the, I guess the epistemic uncertainty to broaden as you would start to do that, maybe?
Yes, because again, you have to pay a price for like the assumptions, and here the assumption of having a larger family of kernels it makes it possible that the data comes from more functions. So you have to pay that with higher UQ at the end. So the more that you want to restrict your assumptions, the sharper your UQ will be. But it's also more likely that your assumptions are wrong because you're having like tighter assumptions.
Hello, Paul. Thank you for the talk. So if I want to do a fully Bayesian version of this, the way I imagine that would look is I'd have some prior over theta, and then I would do something to come up with like a sample of posterior points. And then to produce your green curves, it would just be, there wouldn't be a simple formula, but somehow I'd take that weighted, those weighted data points to construct my green curve. Is that correct? Or is it more subtle?
That's exactly correct. The way I would think about the Bayesian version is exactly this, just having a prior theta in a probability distribution over theta space, and then you could provide the distribution of y over x by doing this kind of average over the posterior. So there's kind of a two-step like base theorem, because there's two priors. There's the Gaussian process, which is itself a prior over function, and then the Gaussian processes are parameterized by theta, and you have a prior over theta.
I guess what I'm guessing here, though, is that in typical scenarios, we might use like MCMC to construct like that sampling from a posterior. Is there anything, it seems like it could be more complicated than that in this case.
I think you could do this with MCMC. The issue is that as you scale to high dimensions, sampling over a distribution in n dimensions is going to be more expensive than what we're proposing here, which is optimizing a problem in n dimensions. So there's definitely issues in like scalability for some MCMC methods. And our goal is to eventually push our method that is based on optimization to high dimensions in a way that should scale better than sampling from n-dimensional models.
Okay. All right. Thank you.
So, do you mind going to, I think it was your first discussion slide at the end?
This one?
Yeah. So here, so this second bullet point, I think is really interesting. And it's something that I've thought about a lot, of the fact that you're not trying to minimize uncertainty. It's not like a squared error or an accuracy, right? That you're trying to optimize, but you're trying to get it the uncertainty to be correct. So I'm wondering, do you know of like any metrics that can quantify like the quality of your uncertainty, kind of in the same way that like RMSE quantifies the quality of your predictions? And in particular, ideally for, real data sets as opposed to, on simulated data sets.
Yeah, that's a great question. In practice, it's hard to compare like different UQ methods if they make different assumptions, right? So even if you had a metric, you're kind of not comparing fairly. But even if you have methods that all, like in principle, if you have methods that all have the same assumptions into account, the best thing that I think we could do is having some kind of expected length of the UQ at a fixed level alpha. So you'd want like the intervals to be as small as possible while taking the assumptions into account and while still being, say, 1 minus alpha level coverage.
Okay, so you're saying like as long as they meet that coverage level, then just pick the one that is the smallest.
Yeah, but the caveat here is that, for example, in this picture, you cannot say blue is better than green, right? Because blue is assuming something which is stronger. So you also have to be careful about this other axis, which is the assumptions.
Mm-hmm. Okay, thanks.
Sure.